Hi, good day everyone. Today I'm gonna share to you the history of math in these two specific subtopics, the decline of Alexandria and the Arithmetica, Diophantus number theory. Now, we might be able to grasp a lot of things here since we're going to take up the roots of the connection of these two subtopics in the contribution of mathematics. Now, what is Alexandria? We might ask, what is Alexandria? Is this the name of a person? Is this the name of a place or thing or anything? Or maybe you might say this is kind of food, but no, this Alexandria is a kind of library. It is the greatest collection of knowledge established by Alexander the Great. Because Alexandria is like a Google in their time. It's very big. It contains a lot of books, a lot of scrolls. Maybe that time there were scrolls in respect of sciences, mathematics, technology, and literature. Everything was there. And it is a very it's like it's as big as a city. That's how big their library is. So you can see it here. This is this city. Alexandria is located in Egypt, and this is how big the library is. Well, you might notice why that Alexandria was located in near the port, because a lot of ships are going there, and then they're trading and they're giving. It's very fast and accessible in gathering information if you're near the port, since every time a ship arrives, they will deliver their books and any other educational materials. Alexander the Great wanted to build an empire. This is the history of Alexandria, an empire of knowledge. Yet he did not long to see it. He died at an early age, even though he was very powerful. He didn't die in war, but he died in sickness. But uh, his long time dream uh, he never saw that long time dream. But good thing, Ptolemy the First was there to fulfill that dream of building an empire of knowledge. Now, Alexandria attracted the minds of Greek, not only the great minds of Greek, but also the great minds of people around the world. Scholars, wise men, all over the world came to Alexandria. Moreover, to encourage more people, smart people, to go to uh, to go uh, to Alexandria. Ptolemy is giving scholarships to those sponsorship to those researchers. We call them researchers today, but at the time, maybe they don't have those words yet. They don't have those kind of terminology yet. But maybe that time Ptolemy is giving sponsorship to researchers, to scientists who is going to library to Alexandria to contribute Alexandria, to contribute the vast knowledge of Alexandria. So there, Ptolemy is giving them free food, lodging, and other expenses. And thus, a lot of philosophers, mathematicians, astronomers, scientists are staying in Alexandria. They dedicated their lives in doing a lot of research, conducting research in Alexandria. It is a very big, what to call that? It's a very big convention. It's like every day there's a convention in Alexandria. Now, Ptolemy the Third, as time goes by, right? As time goes by, Ptolemy III initiated a law that every ship who wants to trade must present their books to be copied, since the rulers of Alexandria is not contented on their situation, but they wanted to make it vast, to make it more innovative than the past. So this new ruler, Ptolemy III, made a policy, a local policy in the land of Alexandria, that every time a ship arrives, they must present their books. That is their way of passing that route. They must present their books to be copied by the scholars. They received a lot of kinds of books in terms of science, mathematics, technology, literature. Some others are comedy or tragic and any other kinds of books. But because of this, Alexandria expanded more and more. They have hired not only that they rely on that policy, but they have hired book hunters who would scout for new knowledge. They would go to other places of the world, and then they're going to gather information, gather new science discovery, and would contribute the would contribute the knowledge that is stored in Alexandria. But through time, since they have gathered a lot of books, they have gathered a lot of things in Alexandria, they have discovered that now presently, they have discovered that Eratosthenes, sorry for my pronunciation, Eratosthenes is a Greek mathematician, physicist, and they discovered that long before Magellan or Christopher Columbus have discovered that the world was round, Eratosthenes already knew that the world is round. He even calculated the diameter of the Earth, of the planet Earth, of our world, of our Earth. He really calculated it way before these two great men. These two great men declared that the world was round, and that's a great accomplishment, right? That is a great accomplishment. Secondly, is Heron of Alexandria. Heron of Alexandria is very advanced in his age, in his time, that he invented a steam engine thousands of years before making the steam engine as an industrial machinery. So I think this Alexandria is very advanced. Alexandria has acquired a lot of knowledge in the world, and that they are very innovative. They are always expanding their knowledge. Now, for 300 years, the library was thriving. But in 48 BCE, Julius Caesar sets the ships on fire. Despite of this post-destruction, destroying part of the scrolls, scholars still visits Alexandria. So their time came up that there's a war, because at the time it's prone to war during this era, right? During this era, it's prone to war, it's prone to sieging places, and Julius Caesar conquered this place, and he put the ships on fire. And apparently the Alexandria Library was on fire. And it is quite sad that some of the manuscripts, some of the scrolls were destroyed, those very vital scrolls, and they could have been very useful today. But despite of that, that's not the end of Alexandria yet. But despite of that, scholars still visits Alexandria. So you can see it in the picture that it's very, this is just an artist's depiction of what happened there. This span of years, Alexandria was operated by different groups of people, and the population of Alexandria became a mixed with different cultures: Greeks, Jews, Romans, native Egyptians, and even Arabs. But the problem is that this led to chaos since Alexandria was not already dominated by the Greeks. They have been dominated by different kind of people. They're now dominated by the Romans. Later on, they're dominated by the Christians, sometime by the Arabs, and now there's a mixed culture in Alexandria. And you know what will happen in a mixed culture society? That there could be chaos. There will be a misunderstanding among themselves, and it's quite sad that this led to chaos. This led to riots and some other hating, and then it made a very unhealthy environment. So the 300-year reign of the Ptolemies, it gave way to an era of street riots, political confusion. Thus, intellectual and commercial glories of Alexandria slowly deteriorated. Alexandria became, some of the people, some of the scientists were killed because there are prejudices that arise. So it's very, it's now very chaotic. Again, I would say, I would like to emphasize it again as described by the book of David Burton, that it's very complicated. The things that are going in Alexandria is complicated. During the span of these years, it ended up scholars being killed as new rulers, since it's not only the Ptolemies 300-year reign has ended. So there are different kinds of rulers that ruled Alexandria, and they saw Alexandria as a threat, not as an advantage. That those people who knew better might be a threat in their political career, might be a threat in their because maybe at the time, in my personal input, maybe at the time they don't want that people would be smarter than them. They might know their anomalies, but probably these rulers don't like that. Maybe there would be an uprising that would happen if Alexandria will still continue. And sad to say, one of our greatest mathematician, Hypatia, she's a mathematician and a martyr, and she was one of the examples of why she was one of the examples of one of the scholars that was killed during at that time. She was killed for reading the ancient knowledge of mathematics and astronomy. It's very absurd that once this place whom you are free to get information, you are free to learn, you must have the happiness to enjoyment to get knowledge, but it ended up becoming a bloody. And Hypatia was supposedly she was a very good, bright mathematician, but she was killed by the Christian mobs. At this time, Christianity is chaotic as well. I'm not saying that, I'm not blaming the Christians, but They did this as a retaliation of what was happened to them before, because they were persecuted, deprived from their rights, and now they got their rights. They became rulers of this place, and this is a kind of retaliation. And so uh, Hypatia was very advanced on her age and her era, that uh, today it is true. Her findings would be true, that uh, but at her time it was false. She could be charged as heretic if she would say that the earth was round, the earth is not the center of the universe. That those statements could be found as heretics during at that time. But it's sad to say that Hypatia was killed. But this indicates that Alexandria deteriorated once the greatest uh, pool, once the greatest. It's like a monopoly of knowledge. It should have been evolved until today, but what happened was it turned out very bad, chaotic, and it ended up in nowhere. If you see today, Alexandria has a very small ruins left. We don't know which exactly the exact location of Alexandria. We have the location of Alexandria, but we don't have already the structures. We don't have but archaeologists found out about classrooms. They knew that they have classrooms, con, convention centers maybe there, but uh, it's sad to say that it's not just the building that was lost, but the contents of Alexandria, the books that could have been contributed, that would make us advance more if they were preserved. Now, on uh, the second topic, it is connected to our first topic, which is the Arithmetica. Arithmetica was one of the books that was originated in Alexandria. It was authored by Diophantus of Alexandria. Diophantus is a mathematician, and thanks to the Byzantine copies, those people who live in the Byzantine era, that some of the book's knowledge were preserved. Good for them that they have preserved this knowledge. And this book was written in Latin. I don't know how to read Latin, but it was translated into English, and it's entitled the Arithmetica. So we're going to have a deeper study on what is this Arithmetica. Let's first know who was Diophantus. No, Diophantus is the father of algebra. Now we have this early information already that the Arithmetica is a book of algebra. I think this is the very first book. It is indeed the very first book of algebra. Since Diophantus is the father of algebra, no one has ever invented algebra except Diophantus itself. He was the first one who created algebra. Born in the year 200 AD approximately, because we don't know really when Diophantus was born, when he was, because of the lost records, it's very difficult to track him. But it is just an approximate, and died around 284 AD. He is said to be a Hellenistic Greek, but possibly an Egyptian, a Jewish, or even Chaldean, because even though he has a Greek name, but he lived in Egypt, so probably immigrant parents, or because Egypt before was once a territory of Greece, and yeah. So his life was not in detail, but we could possibly know his age from an epigram. This epigram is very known, actually. It's very known. Oh, sorry. This one. His boyhood lasted for 1/6 of his life. His beard grew after 1/12 more. After 1/7 more, he married, and his son lived to half his father's age, and the father died 4 years after his son. If x was the age at which Diophantus died, the equation becomes like this, right? So 1/6 of his life plus 1/12 more and 1/7 more. You see, his boyhood lasted 1/6 of his life, 1/12 more plus 1/12x, 1/7 more he married, and his son lived to half his father's age, and the father died 4 years after his son. If x was the age at which Diophantus died, the equation becomes like this. So you see, Diophantus is already, despite of no early, he was curious on how to find unknown values, and he makes this kind of problems. It is a good indication. It is a good uh, curiosity, actually, that because of this he made algebra. So this is actually a very famous epigram, and now Diophantus created a system on how to solve this one. So he was actually able to solve this, or I mean, this is just an epigram, and he wanted to know that people uh, could could know his age through this. So if we are going to find the x, then the Diophantus age should be 84. If we solve for x, yeah, I don't need to detail this one, I think. Yeah, but in what year or even century is not certain. That's supposedly uh, Diophantus could have put what year it could have been, right? So he should have put an epigram again to which year he existed, but he just stated his age. Not only this one, actually, he has created this book, Arithmetica. It's the earliest book dedicated to algebra. So we don't know. Maybe there's more early book than Arithmetica, but this is the only book that gives that presented algebra. So this book comprises of 13 books, and all in all, yet 6 were preserved. It has an assortment of problems and solutions. You see, uh, even though there were only 6 books, but he was able to present the algebra in a good way. Later on, we will discover more. Before Diophantus, algebra was rhetorical, which means the results were achieved by verbal arguments. No notations were invented at the time. It's uh, it's very wordy. Algebra is very wordy. I think it is not algebra, or maybe that is algebra, but it has no notations. I don't know how to call that, but in a modern world, in our modern society today, it is not algebra if we don't have those notations. It is very rhetorical, and it's just plain words that for example, I will give an example of rhetorical algebra. Twice the age of my father. We don't have notations for that. So my age is half the age of my father. So they would just think directly, instantaneously. Okay, your father is 40, so you are 20. So it's very rhetorical, as I say. But uh, but Diophantus wanted to syncopate algebra. He wanted to make shorthand for expressing much used quantities and operations than of abstract symbolism in our sense. He wanted to make it unified. He wanted to make it like there should be a language in algebra, not just a very very vast. Okay, the algebra in this, it must be. He wanted to make it a uniform, that there is a language in algebra itself, and he syncopated algebra, making shorthand, making notations, which would help us also. Notations would help us also in solving the unknowns. Because if it is rhetorical, it's very difficult. Even a normal person cannot solve it. Maybe those high geniuses only, but since Diophantus syncopated it, then it made it a very precise. It made it a very concise, very arranged, very elegant way in presenting mathematical statements. So let's see the Diophantus symbols. So this is X. It looks like S, right? It looks like S, but this is X because Diophantus is using Latin scripts. This is X. This is how he writes X squared. It's a triangle form. It's like a shape of a change of something, a change of the power of Y. I don't know, but this is how they write it before. And X cubed, this one, this X cubed, and we can see it here. It ended here. It ended to X cubed, and then he makes a combination when he reaches X to the power of 4. This is a good what you call that? This is a good indication that algebra can stand itself without using a large number of notations. It is just a combination of something. So at this time, I'm not telling in the modern times, but at this time. So for example, the export, it became export because this is X squared, and then they square a square. So Diophantus has already knowledge about exponents, right? The rules of exponent, that X squared, let's say X squared, that is X squared, and then to the power of 2, because you square, but it square the square. And Diophantus knew that this is X4. So that is X4. It's like, because this is the square, he squared the square. So at this time, Diophantus already have as a knowledge about this. And then X cubed. So this is what I was amazed that Diophantus was able to not only to write another notation for X5th, since Diophantus not go beyond the 5th power, since his problem doesn't require him to solve higher degrees. He has only 1, 2, 3, 4, 5, but he didn't make another notation for these 5 values since he doesn't use 6th degree. But he has already, I think he has a futuristic mind that we can make more than 5th power, and by using combination of these numbers. So square cube, he cubed the square multiplied by the cube, and it is X5th. He knew that one, so he just made he has, I think, that the knowledge of exponents. So X squared multiplied by X3 X cube, because square cube, this is square multiplied by a cube, and it became X to the power of 5. You see that Diophantus has a has a uh, has a knowledge about this already, and he he good thing that he created this one, and then now we have already, he was the one who originated these things actually, but now thanks to him that we're able to uh, establish the algebra that we have now. So in proceeding, uh, Diophantus is not only concerned of a single variable, or I mean in one terms, but he likes to combine terms. He has combination of terms as well. So Diophantus did not have addition sign, but only the negative sign. What he did instead is to group the positive values and separate them with a separator. So this is the separator. Now, example, I have an example here. 35 x cubed plus 12 was written before us. This one. This is 35. They put the variables first, the unknown variables. So x cubed. So x cubed 35. We'll read it 35x cubed. And m, this is just a unit. So the way they put addition, separate the numbers is through putting unit. So 35x cubed plus 12, m12, and is 12. This is a constant. So in separating constant, they just put a unit. What kind of unit? So if we say, let's give an example. What if let's say x cubed plus x squared minus x plus 3. For example, this one. So it could be written as we will put first the positive sides, right? X cubed plus x squared plus 3, right? Plus 3 minus x. So in the earlier times, they could have been written as this. Oh, sorry, I don't have eraser. They could have been written as this. Okay, this is x cubed, and then x squared. Because if we're going to we can put m. I have seen m x squared, because if we're going to stick them together, it will become x to the power of fifth. But what we wanted is just to like that. So yeah, and then m3, and then we have a separator x. So x is an s like that. But we are not concerned about this, because according to the book, it is not really it's not really very clear. But because I've searched some in the internet, there are a lot of variations of of writing. Maybe through time, maybe Diophantus is making this kind of notation. Then through time, he realizes that this is, I think I have to make this notation again, because he's developing this kind of mathematics. But I'm so sorry if I have made maybe I've made some errors here, because if we're going to put this up, it will become. But the concept is here, right? The concept is here that this is x cubed and x squared as 3, and then we separate it with the separator as m is just a unit. It is not a separator. But what we did, the concept is here, right? That we group the positive and then we separate the negative. Now, there's a certain problem in the book of Diophantus. He stated it in his 5th book that he called it the impossible problem. He called it the absurd problem. I don't know how absurd it is today, but the problem is just 4x plus 20 is equals to 4. Considered by Diophantus as absurd, since Diophantus has no idea what negative values are. Why? Because the solution for 4x plus 20 is negative 4. So if we're going to solve it, like, I know that you can solve this one, 4x plus 20. Maybe, I don't know if Diophantus has, I think Diophantus has a system of solving this one. And when he reached this far, maybe he said, oh, how can I minus 4 and 20? This is a negative value. Diophantus has no idea of negative values. He don't know. He doesn't know what is negative 4 at the time. I think he doesn't even know what is 0. Indians created 0, but I'm not sure what time. Maybe Diophantus has already knew that 0, or I think he doesn't knew yet because the Indians created 0 and it was created maybe years later than Diophantus. But I'm not sure about this information. But the thing is that Diophantus was, we can see that Diophantus is not yet ready for this kind of things. It's quite ironic that algebra was already created without establishing the numbers, the integers, that we have negative values, we have positive values, and we have 0. Because in elementary, we knew first in our elementary days, we knew first things that we knew is the negative values, the integers, right? The negative one, we knew that one first, and then later on we proceed to algebra. But during this time, algebra was created first than the negative values. But I think the established, I don't know, it's just unfortunate for Diophantus that he doesn't know the negative values. He could have known it, then he could have been solved this one, or he could have been innovated the algebra more. Now, let's look for different problems that was stated in Arithmetica. So let's take a look for the problems in Arithmetica. Here, book 1, problem 17, find 4 numbers such that when any 3 of them are added together, their sum is one of the 4 given numbers. Okay, I will hide that first. Say the given sums are 20, 22, 24, and 27. Now, if we're going to understand the problem, we're going to find 4 numbers in which these 4 numbers, A, B, C, D, we will add a different kind of combination of A, B, C, D, and their sum are one of these 4 numbers. Example, A plus B plus C, the answer is 20, or B plus C plus D, the answer is 22, like that. So if we add these 4 numbers, any 3 of these 4 numbers, then the sum is one of these 4 numbers. So it's like a combination of 3 numbers out of 4 numbers. Then the answer should be 20, 22, 24, and 27. So let's say the sum is x. Okay, let's say that the sum is x. Then the numbers are just x minus 20, x minus 22, x minus 24, x minus 27. Because the sum is x, and then we wanted to know what is this number. So for instance, if equation 1, okay, for equation 1, x minus 20, we add it to equation 2, and we add it to equation 3. Equation 1, we will just call this the first number, the second number, the third number, we add them. And then the answer is 1 is 20. And 20 is one of the given 4 numbers, one of the given sums, right? Then we add the fourth number on both sides of the equation. Then it will become, the fourth number will become x minus 20. So it follows that, okay, I will just continue. It follows that, I hope that you already knew the concept, but it follows that x is equals to x minus 20, x minus 22, x minus 24, and x minus 27. So these 4 numbers, because we wanted to know what is the value of this x, and then we will know what are the values of these 4 numbers. So we use algebraic operations, and we ended up to have x is equals to 31. Hence, plugging numbers, the required numbers are, we will plug 31 to x minus 20. So 31 minus 20, 31 minus 22, 31 minus 24, 31 minus 27, and we have 11, 9, 7, and 4. Now, let's check if these 4 numbers really satisfies that any 3 of them is the result is one of these 4 numbers. Now, the combinations, we will use the combinations, right? What could have been, how many combinations in 4 values? So we have, if we have basic, this is in probability with combinations. I learned this in probability and statistics in high school. And if we have n values, so we have n factorials, and then r factorial, that is the number of repetition, number of 3. There, 3 is our r, and then the number of values, we have 4 of them. So n minus r, and then factorial. So we have 4 factorial over r. What is our r? This 3. And then n minus r is just 4 minus 3. 4 minus 3 factorial. Four minus 3 is just 1. So we will just remove that 1, right? 4 factorial. And then 4 times 3 factorial. And here, we can now remove this 1. And we have 4 combinations here. We have 4 combinations. So let's see. What are these combinations? 11, 9, and 7. The answer is 27. Is 27 here? Yes, 27 is here. It's correct. It's verified. Next is 9 plus 7 plus 4 is equals to 20. Oh my God. Yeah, this is 20. So 20 is one of the 4 numbers? Yes, it is. 20 is one of the 4 numbers. 7 plus 4, 13 plus 11. 7 plus 4, 11 plus 11, it's 22. And 22 is one of these 4 numbers. Lastly, 4, 11, and 9. Are we repeating numbers? No, we are not repeating numbers. So 4, 11, and 9. 24 is here? Yes, and it is verified. So therefore, the solution of Diophantus is correct. You see that Diophantus was able to achieve these difficult problems with the use of his new discovery of algebra, with his new solving, making algebra. And we can see that he is successful in establishing algebra, even in a very crude manner. It is not well established at this time compared today, but we can see that he was able to solve this kind of problems. Now, number 2. In the book 2, problem 20, find two numbers such that the square of either added to the other gives a square. So what we want is find two numbers, the square of either added to the other gives a square. So example, A and B. A and B are two numbers. Okay, A is another number, B is another number. So if we will square A squared plus B is also a square. Likewise, B squared plus A is also a square. So either one of them is a square and added to a normal one, it gives a square. You see, Diophantus chose x and 2x plus 1 as numbers because when we add them together, it will be automatically be a square. The square of the first number, because this is the first number, x, and the second number, 2x plus 1. Of course, x squared plus 2x plus 1 is a square of x plus 1. Quantity of x plus 1 square, that is equivalent to x plus quantity of x plus 1 square. Now, let's move to the second number. The square of the second number added to the first number. 2x plus 1, quantity of 2x plus 1 squared plus x, and that is 4x squared plus 5x plus 1. The problem is here. This equation here at the right-hand side is not a square. It is not written in square form. I mean, in factorial way. In a way, it is not a square, right? It's not a square. So, but what we have to do? What did Diophantus do? To make this expression to a square, Diophantus assumed and equate this into 2x minus 2 squared. So he assumed this one. He make assumptions that 4x squared plus 5x plus 1 is equals to 2x, quantity of 2x minus 2 squared. So since this is just an assumption, the same effect would take place if we use 2x minus 3 and 2x minus 4 instead of the one that we used. So Diophantus just used this one, but we can also use these numbers. Now, this is the resulting is not a negative number nor 0. The x should not be 0 or a negative number. So Diophantus just wanted to, not wanted, but he was able to solve this one in positive numbers only. So he equate this to 2x minus 2 because he wanted this to become a square. So he's making assumption. He's forcing it to become a square. So 4x squared plus 5x plus 1. He's using 2x so that he can eliminate the 4x. You see? Okay, we can eliminate the 4x squared and then 13x, and x is equals to 3 over 13. What happened? Hence, substituting x and 2x plus 1 results to 3 over 13. This is x, 3 over 13. And then we substitute only 3 over 13 to 2x plus 1. Right? So 2 times 3 over 13 plus 1, it is 19 over 13. So 3 and 19 over 13. So those are the two numbers. But we have to test if it satisfies. So the first number squared, then added to the second number. So we will square the first number. Okay, here. The first number was squared, x squared plus 2x plus 1 is equals to 3 over 13 squared. You see, 3 over 13 squared plus 19 over 13. We square the first number, right? Is equals to, we add them together. I'm not detailing it, but if you try, if you try to add it, it will become like this: 256 over 169, and this is actually 16 over 13 quantity squared. So it satisfies, right? It satisfies the 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 answer satisfies to to what in the problem is asking. So the first number added to the square of the second number. So the first number is here, it's not squared, it is on the second number. So x plus quantity of 2x plus 1 squared is equals to 3 over 13, it's normal, plus we squared the second number, 19 over 13 quantity squared, and it results to 400 over 169. So this is the square of a certain number, which is 20 over 13 squared. So both satisfies, therefore, that 3 over 13 and 19 over 13 is the solution to the problem. And Diophantus again is successful in solving this problem. Now, let's proceed to the third and last problem. This is the third and last problem. And find a number such that if two given numbers, say 6 and 7, are subtracted from it, both remainders are squares. Let us set the numbers. So we're going to set the numbers. Here, this is very easy to comprehend, that if there's a certain number x, if we minus 6 from it, and certain number x, if we minus certain number x, we minus 6 from a certain number x, then it is a square. That same certain number x, we minus 7 from it, and the remainder is also a square. So we will going to set the numbers. X minus 6 is equals to a squared, right? Because it is a square. And x minus 7 is equals to b squared because it is a square. That the method was used here is close in the method in Diophantus's work. So this is almost the same, but because of modern algebra, we're doing this way. But it is almost the same on what Diophantus is doing. So using algebraic identity, it's very familiar, right? Sorry, I showed that one. It's very familiar. A squared and b squared. It's very familiar, and it is if you're dealing with algebra, you know that you have something to do with a squared and b squared, and that is a squared minus b squared is equals to quantity of a plus b and quantity of a minus b. That's the factor of a squared minus b squared, and we can utilize this one. To take the results, let's plug in the variables. So a squared minus b squared, we just put this one. X minus 6 is a squared, and b squared is x minus 7. And we're going to equate it into 1. Why? We'll see it later. Is resolved into two suitably chosen factors from which a and b can be obtained. If one takes 2 and 1/2 as the factor setting, a plus b is 2, and a minus b is 1/2. This is a. This is a plus b is 2, and a minus b is just 1/2. Right? This is just 1/2. So if we're going to multiply this one, A squared minus B squared, if you're going to multiply that one, that is the same, right? These are just the same. It equals to 1. So satisfies A squared minus B squared is equals to A plus B, A minus B. This is 2, and this is 1/2. Of course, this equals to 1. This just equals to 1. Thus, solving it using elimination. So A plus B is equals to 2, A minus B is equals to 1/2. We wanted to know the values of A and B, and we are now able to know the values of this one, the value of X. So using elimination, I just used elimination, which is very easy for me, and it is very fast as well. So 2A is equals to 5/2. And now we know that A and B, respectively, 5/4 and 3/4. So let's plug in. Let's try. A squared is equals to 5/4 squared. That is 25/16. And B squared is equals to 3/4 squared. That is 9/16. It follows that A squared is equals to X minus 6. Because that is our equation before. X minus 6, A squared is X minus 6. We set it to A squared, and that is 25/16. And B squared is equals to X minus 7. That is 9/16 here. We just took it from here. We just put the values here. Use A squared, and X minus 6 is equals to 25/16. We will just use, because we just want to know the X. So any of this is the same, but I wanted to use A, this one, A squared, X minus 6. It depends upon you. But using this one, X minus 6, we can see 25/16, and X is equals to 121/16. That is the number that when you subtract 6 from it, it is a square. You subtract 7 from it, it is also a square. So X is 121/16. And let's try equation 1. Okay, equation 1. 121 minus 6 is equals to 25/16, which is what? A square of a number. Equation number 2. X minus 7 is B squared. 121/16 is equals to 7. And that is 9/16, which is also a square of a number. And we see that Diophantus was successful. I'm just copying his works. Actually, I'm just copying the method, how he was able to solve it. This lecture is not about how to solve certain problems, because we have already established algebra. But this is to show to you the roots of algebra, how it began, and how it was very useful before, even though it was very crude. It was crude at that time. We can see how Diophantus was a great contributor in the world of mathematics. He was the one who created algebra, established notations that were able to evolve in modern times. And now, despite of in the early stage of algebra, he was able to establish it. He was a handicap mathematically. He don't know the negative values. He don't know zeros at that time. But still, he was able to successfully establish, not fully established, but successfully introduced to us algebra. And in the end, thank you so much for watching this, and I hope that everyone was knew about this new knowledge of the history of mathematics regarding Diophantus. of Alexandria. Thank you.